Okay, so this is the briefing of the sunscreen experiment. We also sometimes call this the Aldol investigation as well, because the key reactions you're doing here is an aldol condensation. Now, this experiment is different to the experiments that you've done before. It's designed to transition you towards doing projects. Projects are much more open-ended. There's more planning that needs to be involved in before you start these types of experiments. The experiments are more open-ended, and there's also the assessment will be different to some of the other experiments that you've been doing as well, where you just simply submit your scan of your lab book and spectra. So in this briefing, I will cover those three main aspects about what you do before you start the experiment, what you do when you run the experiment, and then what you do for your assessment. And if you need to revisit any of these sections again, so for example, after you finish the experiment, you might want to look back at what you need to do for the assessment part of this video again, then please please do so. So what you're doing in this experiment is you're taking a cyclic ketone. It will be either cyclopentanone or cyclohexanone, and you'll be reacting it with an aldehyde. And what happens is an aldehyde will react twice on either side. It will do an aldol condensation reaction, helped by some catalytic amount of sodium hydroxide, and it will give this highly conjugated dibenzylidine system. Now, these types of compounds are actually used as sunscreen agents because they've got large chromophores, they've got their highly conjugated systems, so they're good at absorbing UV light. And so, what you're going to be doing is you're going to be doing this experiment as a sort of mini project. You will have been assigned a cyclic ketone, either cyclopentanone or cyclohexanone, and then you've been given two aldehydes as well. And what you're going to do with each aldehyde is you're going to make two of these dibenzylidine products, and you're going to look at the UV spectra of those two products to assess which will have the better sort of properties to be a sunscreen agent. Okay, so it's like a little mini project. You're making these compounds to sort of to see which these compounds can be used as sunscreen agents, and there's two of those that you're going to make, and you're going to compare them. So on Minerva, you will find which cyclic ketone and which two ketones you've been assigned to use. Okay, so with each of the products that you're trying to make, what you're doing is you're reacting one aldehyde on either side. Okay, not trying to have the two aldehydes where you have one aldehyde on one side and the other on the other side. Okay, so each of the two compounds is where you're going to do a reaction where it's one cyclic ketone, one aldehyde that you're reacting together, but you're making two of these compounds, which is why you've been assigned to two aldehydes. And the way that you're going to react it is with the same conditions, with catalytic sodium hydroxide to undergo this aldol condensation with ethanol, and then what you're going to do is you're going to look at the UV spectra of those two compounds that you've made, and essentially the compound which absorbs more UV radiation is going to be the better sunscreen agent, okay, because it will absorb more UV radiation from the sun. So before you start this experiment, there's preparation that you need to do before you start your timetable experiment. You need to find your assigned ketones and aldehydes, and this is on a document that's in Minerva in the folder for this experiment. You'll find your student ID alongside the ketone and the two aldehydes that you've been assigned to. To help you with this experiment, there's a sort of a standard procedure, but you're going to have to sort of look at how well the reaction's working. You're going to have to adapt the reaction and the conditions as is needed for this experiment. So to help you understand what's going on in this experiment and how, if it's working or not, and if you need to adapt it or change it, you need to know the mechanism of this reaction as well. So you need to produce the mechanism of the reaction. It's an aldol condensation, so you need to think about the curly arrows that you would do for reacting your sodium hydroxide to form an enolate, how that enolate then would react with the aldehyde, and how the condensation step would occur to eliminate water to give you the alkene at the end as well. Then also, just like with reactions where it's a project, you actually have to do some of your own health and safety assessment as well. And here, what you have to do is you have to, once you know what your aldehydes and ketones are, you need to look up the safety information for them. So you need to look at the hazards of these experiment of these aldehydes and ketones, and also the sodium hydroxide and ethanol that you're using, and produce a COSH form, very similar to the COSH forms that are given in the experiments that you've been doing previously. And again, this is part of the training that's part of doing this experiment, is to produce your own COSH. And then also you need to then calculate the appropriate amounts of the reagents for the aldehydes and ketones that you're going to be using. And so these all have to be checked and signed off by a demonstrator before you can start the reaction. In particular, that you've got the correct mechanism for the reaction, you've got your COSH forms, some of which need to be signed by the demonstrator and handed into store, some of which you keep yourself, and also that you calculate the reagent amounts correctly as well. You won't be able to start the reaction until these steps have been conducted. The script for the experiment gives you much more detail over exactly what you need to do for these steps before you start. Okay, and then in terms of running the reactions, because you've got these two compounds to make, it's your choice whether or not you want to do one reaction, see how it works, and then learn from that, and then run the second aldol condensation reaction. You'll obviously be quicker with the second one because you've learned from the first one what works well, or you can choose to do both at the same time. Again, you've got the freedom, just like with a project, you've got the freedom to sort of manage and run these reactions as you choose to do so. So the general procedure for running the reaction is you're mixing the aldehyde and ketones together with catalytic base and with ethanol as a solvent. So you'll need, because you've got the aldehyde reacting twice on either side, you'll need two equivalents of aldehyde to your ketone. You're given a general procedure of how to start by sort of mixing the reagents together at room temperature, but the reaction might not work well at room temperature. It might need adapting. So what you've got to do is you've got to sort of monitor the reaction by TLC. It could have finished, it could be complete, but it might be incomplete, it might be reacting poorly. You've got to use the assessment of your TLC to decide if it needs reaction needs changing, so it reacts better to form your product, or if it has complete, then you move on to the purification stage. Again, we haven't told you what sort of purification to do. That's something for you to decide yourself. And again, by looking at what's happened in the reaction, if it needs a filtration, if it needs a liquid-liquid separation, this is where you sort of use the mechanism that you do before you start the reaction, both in the TLC and the purification, to sort of think about, okay, how am I applying this theory here into the reaction to decide how it progresses and how it needs purifying afterwards. Then, so that's what you do to actually run and do the reaction. Then after you've completed the synthesis and you've made your two compounds, this is where you're going to do the analysis to determine which is the better sunscreen reagent. Now, some of this will actually come from your experimental results. You'll look at how the two reactions worked for you. You'll think about how well each of the aldehydes reacted with your ketone, which one gave you the better yield, and that you should factor that into thinking which is the better sunscreen reagent, because you think about, well, which is practically the better, which practically is easier to form and gives you a higher yield. But then you'll also look at the UV absorbance data of these two compounds to see which one would be better at absorbing UV radiation from the sun. So typically, UV light from the sun is between 290 and 400 sort of nanometers. So really, it's about looking at that particular range of wavelengths and seeing which of the two compounds has the stronger UV absorbance. Okay, so I've got an example of some UV data here then. You can see that across that range here, we've got a set of compounds that are absorbing UV radiation, and the ones which are better sunscreen agents will have higher absorbance. So if you sort of overlay the data, for example, you'll be able to compare the two, and in particular, make sure you're focusing across that sort of range between 290 to 400 nanometers. The one which has a stronger absorbance should be higher across your sort of y-axis, and this is how you can determine if which of your two compounds has absorbed is a better sunscreen reagent. So for this experiment, the UV data is provided for you on Minerva for your sunscreen agents. Okay, you make sure you look at the data that corresponds to the ones that you are making. You sort of plot the data, either at Excel or Origin as you choose, and then compare the UV absorbance. Make sure it's UV absorbance across the range that I've indicated before that you're looking at to see which is so to make sure it's focused on UV radiation from the sun, and then compare the two and see which one is stronger to see which is the better sunscreen reagent. Okay, so that's the kind of analysis that you'll do after the experiment, and that's the end of the experiment. Then you'll have made two sunscreen agents. You will have looked at how well they worked experimentally to form. You'll also then looked at their UV data to see how well they absorb UV light, and you'll use that assessment to decide which is the better sunscreen reagent. And then what you can do then is you can write up the results of this mini project as a report. This is a standard way in which you write up the results of a project. And so the report that you do for this experiment is the sole piece of assessment that you'll do for this experiment. So you don't need to submit post labs of your sort of samples or yields and your scan of your lab book. You're just simply going to write this experiment up as a report, and this will be the sole assessment for the experiment. The deadline will be on Minerva. The guidelines for how you write the report will be on Minerva as well, but it's the same format that you will have used for Priestley reports before. So when you've written Priestley reports for other experiments, that's where you've had the training on how to write these types of reports. Okay, now you're sort of using it to write up the report for this particular experiment and future projects as well. So it will have the standard format. There'll be an abstract, introduction, results and discussion. It should be a conclusion experimental section as well. And all the report guidelines that are on Minerva about how to write these reports are exactly the same as what you will have to do for this experiment. So a couple of areas of your report I want to focus on. The introduction. The introduction should be fairly brief. We don't want to give for you to write lots in your introduction, but what you should do is have a little bit of background in there, and aims as well, which kind of gives you then the context as to why you're doing this sort of mini project. So in terms of these are sort of the points that you want to sort of be writing about, in terms of the background, that what kind of makes a good sort of sunscreen agent. What are the common sort of sunscreen agents that are used? Like what other compounds are used before? Okay, that helps the reader understand, why you're sort of making these compounds, because this is the work that's been done before that shows these other compounds, these other properties make good sunscreen agents. Therefore, these compounds that you're making should also be good sunscreen agents as well, and this is why you're trying to make and analyze those compounds. So there's a sample paper on Minerva where you can get that information from. Okay, so you don't need to write up everything that's in that paper in your introduction. It's really within that paper you'll find the information for these sort of two sort of points, on the key points about the background to why you're doing this mini project. And so you don't need to research or find any more papers as well. It's just this one paper that will have all the information that you need in there as well. And then in terms of the results and discussion, okay, these are kind of, again, similar things that you will have had to write up in other laboratory reports as well, but just sort of re-emphasizing these points for this report as well. So you need to give a general mechanism. What I would say is, because it's the same mechanism for the two compounds that you're making, you don't need to give the mechanism for the first compound and then just give exactly the same mechanism for the second compound because they're the same. Just give one generic mechanism saying, this is how both sunscreen agents are reacting and this is how they form your product. Highlight key things like, these are perhaps intermediates that you would see in the reaction. Try and link it to how you're running the reaction. So, why you're using that sodium hydroxide as a base, for example. Why is that okay to use? You don't need to go into more detail. You don't, for example, beyond just say like this is the mechanism, relating it to the practice of the reaction. You don't need to talk about like HOMOs, LUMOs exactly to say like why things are reacting between like the enolates and the aldehydes in terms of orbital theory. That's perhaps a bit more detail, but just sort of briefly explaining why they react together. Then it's also really important that you talk through your experiment as well. So, describe how each of the two compounds, how they were stirred together, what the TLCs were showing you, if you change them, how you change them, the reactions, and link it to the theory, link it to the mechanism. Say like, if you think the TLC was showing the intermediate, say that. If you think it was showing the product, then obviously again give your reasoning and rationale for that as well. So that links to the next point. Then relate to theory to the practice. What you can observe or see in the reaction. If it goes a certain color, does that help you understand what's happening in this reaction? If you form a precipitate, why is it forming a precipitate? That kind of thing. Then a brief discussion of your sort of final product with the IR and NMR analysis. So you don't need to talk about all the peaks in your compounds, but what are the key peaks that show that you've made your two sunscreen agents in good yield, or if you've got a starting material, what are the key peaks in the IR NMR that show that you have starting material present, or starting material is definitely not present in your final products. And then also compare the reactivity of the two aldehydes. So you'll have the yields of your two reactions. You'll also note how well they react, which ones react faster than the other, for example, which one might have worked well at room temperature, which one might have needed heating for it to react. So compare the reactivity, discuss, and again, hypothesize why you think one aldehyde might have reacted more readily with your ketone than the other, and discuss that, and again place that in the context of the aims of what you're trying to do in this project. Which one you think would be the better sunscreen agent to use, because which aldehyde is basically more reactive, forms higher yields, etc. And then also discuss the UV data as well. So plot the data, discuss and show the absorbance of the two compounds, and then sort of again give your analysis in terms of which you think is the better sunscreen agent. So do make sure that you do conclude your results and discussion by sort of discussing and saying, at the end of this, your results and discussion, therefore, based on the experimental results and the UV data, this is what I think is the better sunscreen agent. In terms of the experimental section, same format, standard procedures for writing your experimentals. Just to highlight, make sure there's two procedures, one for each compound. Make sure the data that you have, goes with each procedure for each compound, so you're not combining it all together as well. So just that third point there. Make sure the reported data it matches with each synthesis, and then the conclusion section at the end, just summarize the key points and don't put in new information. So the key thing here really is, don't use a conclusion to say, but this is the best sunscreen agent based on analyzing your data for the first time. Have that analysis in your conclusion section, in your results and discussion section. Your conclusion is just about reiterating those key points. Okay, so that's the briefing with the Aldol sunscreen experiment. Okay, so covered different sections, what you're doing and why you're doing it, what you need to do before you start the experiment, what you need to do when you're running the experiment, and what you need to do in your analysis afterwards, and what you need to do for your assessment in terms of writing this report. Okay, there's lots of different sections. If you do need to revisit any of these sections, again, do make sure you do so. It's all contained here within this briefing video.